This topic will cover how to calculate values associated with continuous random variables, including the mode, median, the lower and upper quartile, the mean, the variance, and the standard deviation. The mode of a continuous random variable is the x value that would give us the maximum value for f of x within that range of the probability function. If we had a graph of a PDF, how could we find the mode? We could potentially use differentiation for this to find the maximum value of a graph. For each of these two PDFs, we're going to use differentiation to find the mode. You may want to pause the slide now to see if you can find this. So for f of x, we have a function here defined between 0 and 1. We can differentiate the function, and setting this equal to 0 gives us two x values. We can then find the second derivative and then use this to determine which is a maximum and which is a minimum. If you do this, you will find that 0.789 produces a maximum. So we can say that the mode is 0.789. Now for g of x, if we follow the same pattern, we're going to differentiate the function to get a local maximum. If we differentiate, we'll get two x values again, and the value we get is 0.136. You would use the second derivative to determine that this was a maximum. So again, we could say that 0.136 is a local maximum. However, it turns out this is not the mode. Consider why this might not be the mode of g of x. So when finding modes, we need to be careful, and sketching the graph can always help determine what's actually going on. So for f of x, this is the function here between 0 and 1, and we can see that the local maximum that we found was indeed the highest point on the curve within that range. So this was the mode of f of x. The g of x, however, although there was a maximum and a minimum within that range, and we found the maximum as x equals 0.136, it turns out that there is actually a point that is higher on the curve within that range than the maximum itself. Remember that a local maximum just means that it's the highest point within that local area. It doesn't mean it's the highest point on the entire curve. So you also need to be careful here. If you check the endpoints, if you substitute in this case 0 and 1 in for x, and if they give you a higher value of f of x than when you substitute x into g of x up here, then one of the endpoints may be the mode rather than the local maximum. So substituting in 1 actually gives us a higher f of x value in here. So therefore the mode is 1. The mode of a continuous random variable is the value that gets the maximum value for f of x within that range. Differentiation can be used to find the mode of a PDF, but you always need to check the endpoints as well, because these may be maximums without being stationary points. They may be give a higher value of f of x, but not have a gradient of 0, so therefore they wouldn't be found by differentiation. Next, we're going to find the median, sometimes known as Q2, of a continuous random variable. The median is the x value that satisfies this here. In other words, if we were to integrate the function, starting from the lowest possible value that x could be, negative infinity, and going up to that point, x equals Q2, if the area is a half, then this represents the median. This is saying that it is the vertical line that cuts the area exactly in two, so that there's a half on each side. Alternatively, you could find the value so that if you start with x being Q2, and go to the highest possible value x could be, positive infinity, you would also get an area of a half. In other words, the area is a half on both sides of that vertical line. So another way of expressing this is that the probability that x is less than or equal to Q2 and the probability that x is greater than or equal to Q2 are both a half. A similar technique to this can be used to find the lower quartile and the upper quartile, except instead of the area being a half on each side, we would have a quarter on one side and 3/4 on the other. So for the lower quartile, the area from x is negative infinity up to the lower quartile would be a quarter, and then the area from the lower quartile up to x is positive infinity would be 3/4. And then these values are reversed for the upper quartile. So in other words, the area to the left of the upper quartile is 3/4. The area to the right of the upper quartile will be 1/4. For each of these PDFs, we're going to sketch them and then find the median and the quartiles. So here's the function for f of x. It's defined between x is 0 and x is 2. We're going to find the median by integrating from negative infinity, but in this case we're just going to integrate from 0 up to q2 because 0 is the starting point for the function. I'm going to set that equal to a half. So we're going to integrate the function from 0 up to, we're going to call q2 m for median. Integrate this function, set it equal to a half. If we were to calculate this by finding f of m minus f of 0, set this equal to a half, we're left with a cubic equation. We could use the calculator cubic solver for this. We find an m value of 1.238. Now we're going to follow a similar rule for finding the lower quartile, except we're going to find the integral from 0 up to s, and we're going to set this equal to 1/4. Integrating this gives us a similar cubic, and solving this gives us an s value of 0.8248. And finally, for the upper quartile, we can find the integral from 0 up to t, and we're going to set that equal to 3/4. This gives us a cubic, which has a solution of 1.611. For the second function, here we have a function made up of two straight lines. If the PDF is in different sections as it is here, you may need to determine which section the median and the quartiles lie in first before you continue with the calculation. So finding the area of the first section, we get 0.6. Therefore, we know that the lower quartile and the median will be in the first section of the PDF. We also know the upper quartile will be in the second section of the PDF. So to find the median, we're going to find the integral up to m and set this equal to a half. Again, we can integrate from 0 because this is where the function starts, up to m. Set this equal to a half. This gives us a solution of 2.739. So the m value is here. Similarly, we can find for the lower quartile the integral from 0 up to s of the first function, set this equal to a quarter, and solve this to give us a lower quartile of 1.936. And finally, for the upper quartile, we know that the upper quartile is going to be in the second section, so we can either integrate the first section and part of the second section and set this equal to 3/4. Alternatively, we could integrate from t up to 5 and set this equal to 1/4. This would give us a similar solution. So in this case, the integral needs to be split into two functions. First, going from 0 to 3 of 2x over 15. We already know that this part is 0.6 because we calculated it earlier. We're then going to integrate from 3 up to t. This is the second section, and the whole sum of this will add up to 3/4. So we can rearrange this. We can now see that the integral from 3 to t of the second function has to equal 0.15. This is because we had 0.6 already on this side and 0.75 on the other side. By rearranging, we're left with this integral being 0.15. Again, we're now going to find f of t minus f of 3, set this equal to 0.15. Calculating this gives us this function here, which has a t value of 3.419. So alternatively, to find the upper quartile, we could have used the rule that the integral from t up to infinity was a quarter. So in other words, the area to the right of that point was a quarter. In this case, we don't need to go all the way to infinity. We can just go from t to 5 because we know that this is where the function stops. So the integral from t to 5 of the second function has to equal 1/4. Therefore, integrating and finding f of 5 minus f of t, setting it equal to a quarter, gives us the same equation and therefore the same solution for the upper quartile. We've seen previously that the mean of a discrete random variable, sometimes known as EX, the expected value of x, can be calculated using this formula. It's the sum of each of the x values multiplied by their probability. So for a continuous function, we could estimate this by using rectangles with a width of h. So the expected value in each case will be the probability, which is found by finding the area of each rectangle, multiplied by the x value. So an estimate for EX could be the sum of h times f of x in each case. This is just the area of each rectangle, the width times the height, multiplied by the x value itself. We can then use a limiting process to allow the width of each rectangle to tend towards 0, the number of rectangles to increase to infinity. And as h tends to 0, this summation becomes an integral. This leads us to the formula that the expected value of x for a continuous random variable is the integral of x multiplied by f of x dx. So the mean, or expected value, of a continuous random variable is defined using the formula Ex equals the integral of x multiplied by f of x. Other formulas derived for a discrete distribution are similar to the formulas for a continuous distribution. So for example, for the discrete case, we have the expected value of a function g of x can be written as the sum of g of x multiplied by the probability in each case. We've seen this previously. The continuous version of this is the expected value of a function g of x is just the integral of g of x multiplied by the probability function. So integral of g of x f of x. The discrete case, the expected value of x squared can be found by finding each of the x squared values multiplied by their probability and then summing these. The continuous case gives us the expected value of x squared is just the integral of x squared multiplied by the probability density function. And in this discrete case, the variance of x can be found by finding the expected value of x squared minus the expected value of x all squared. The continuous version is the same as this. The variance of a continuous random variable can be found using this formula. This is the same formula as it is for discrete random variables. The standard deviation can be found by finding the square root of a continuous random variable of the variance. So in this example, we're going to start with a continuous random variable x with this probability density function. We're going to find the mean and standard deviation for this distribution. So to start with, the formula for the mean, or the expected value of x, is the integral of x multiplied by f of x. Now, because there are two sections to f of x, we're going to have to find this integral in two parts. We need to apply this across the full distribution, so there may be several sections to this. In this case, the expected value of x is going to be the integral from 0 to 3 of x multiplied by the first part of the function, 2x over 15. We're then going to find the integral from 3 to 5 of x multiplied by the second part of the function, 1 minus x over 5. Integrating each of these and finding the sum gives us a mean of 2.667. We're now going to find the variance using the formula that the variance of x is the expected value of x squared minus the expected value of x all squared. The expected value of x squared is just the same as the expected value of x formula, except instead of integrating x multiplied by the function, we're going to multiply x squared multiplied by the function. So if we integrate x squared times the first part of the function from 0 to 3, and then integrate x squared multiplied by the second part of the function from 3 to 5, we get an expected value of x squared of 8.167. We already have the expected value of x from the first part, so if we square this, we will then have the expected value of x all squared. We can then subtract these two values, giving us a variance of 1.054. We were asked for the standard deviation, so we now need to square root this, giving us a standard deviation of 1.027. Now complete exercises 4b and 4g on pages 60 and 75.